So now we're going to talk briefly about some of the strengths and weaknesses of the various algorithms. And we've talked about each of these in the lectures on these. So I'm just going to be summarizing these strengths and weaknesses of the algorithms that we've talked about since the midterm. Artificial neural networks. You should understand how the networks are made, what the layers are, and that there's an input hidden and an output layer. One of the nice things about AN is that it can map linear and non-linear relationships and also interactions between input variables. And so AN can do that and do a good job of that. Research has shown that with up to around 12 hidden nodes in the hidden layer, and often with even less than that, an AN network can approximate any continuous function. So it's an amazing learner. In our class, we were often getting very good results with 3 to 5 hidden nodes and 1 or 2 layers. There has to be a random starting place for the weights on the lines, and so then the algorithm has to learn from a starting spot. So generally speaking, what happens with AN implementations is a random starting place is given for the weights, and then they are iterated in terms of improving and strengthening the relationships, and those that seem to be the most predictive are given more weight, and those that are not really helping with the prediction are giving less weight, and so that's how AN does it. So we have to do a number of tours, a number of different starting spots usually to find a good model. The input layer in an AN is where the input columns or the input data actually is. The hidden layer is the intermediate layer, and the output layer is the value of the outputs. And so this is what a neural network typically looks like. Sometimes there'll be more than one hidden layer. So this is an example of one hidden layer, but there could be 2, 3, or 4, or 5 different number of hidden layers. Generally in this course we work with just 1 or 2 layers. Now the way a node works inside a neural network is there is a transfer function. So at the hidden layer and at the output layer of a neural network there is a transfer function. So all of the values of the inputs are actually brought in, summed together, added to a random sort of like intercept or random, what they call a bias. Then this entire value is then run through a function. Now this function could be a linear function, and if so, then this is very much like a multiple linear regression. You have like an intercept or a bias, and then you have the weights coming in from each of the input variables. Then this is all summed together and then run through a function. If it's a linear function, then that's what would happen, is that we would have what looks like an MLR. If this is a nonlinear function, like a tanh or a logistic response function, then we still have to have all of these values summed up, and then the sum is given into that function, and then the output is given. So what would be fed in here, for example, in the example of logistic response function, could be the value of legit. And so then this function would be 1 over 1 plus e raised to the negative legit, and then what comes out of that is going to be some value between 0 and 1. It has been empirically proven that the logistic response function is usually not the best function for doing a nonlinear model. The tanh is better. The tanh goes from -1 up to 1, where legit goes from 0 to 1. So the fact that you can have negative values and positive values as your outcome, that is the A that comes out, is helpful, because sometimes you're trying to define something that is a negative or a positive outcome value. And the other thing is that tanh does not tend to get stuck. In other words, it doesn't train to a certain point and then just get stuck and not be able to train any closer or any better, where the logistic response function does tend to get stuck. And this is why a lot of your tools do not put in the logistic response function as a transfer function. Instead, they'll put in tanh or a variety of others. Now, there are many different transfer functions out there. We worked with a couple of them in this course, but in a lot of the tools you can designate different types of transfer functions if you want to. It's usually good to have a combination of linear and nonlinear transfer functions, because if a linear fits the data better, then the weights can be given to that. If the nonlinear fits the data better, then more weights can be given to the nonlinear transfer functions. Here's an example of us putting in different values of of tan, for the tan H function. And so different values for x would go in, and then basically then the outcomes are going to be between -1 and +1.